Today's webinar, how to analyze your data 6 times faster using PyTecplot and the multiprocessing module in Python. Okay, so some background on Techplot for those of you that may be new to Techplot company or just need a reminder. We were founded in 1981 by a couple of Boeing engineers who originally were writing CFD codes, and a few years in they realized they needed a way to visualize and analyze the results of their CFD, and that's where Tecplot 360 came from, and that's grown into the largest and most complete independent post-processing solution in the world. We have about 47,000 users worldwide, and we really are trying to stay focused on the needs of the CFD community. And those needs that we're seeing today are how to process large quantities of data and how to save you time. So to do that, we are looking at big heterogeneous data. So Tecplot 360 has data loaders for many different CFD codes, many different file formats. So that's where the heterogeneous data comes from. People can use Tecplot 360 to analyze CFD results and bring in measured data as well to look at those data in one tool. And the big part of this data, the data are really growing in size with Moore's Law. Data I/O is lagging far behind. We're seeing that CPU speeds are increasing with Moore's Law at about every 18 months, where the data I/O, getting the data off the disk, is only doubling about every 36 months. So we need interesting and novel solutions for loading more data off disk faster. So we've developed a new file format called Sizzle. SCPLT is the file extension to help with that. We're not going to present that today, but I encourage you to take a look at that new file format. Understanding ensembles of data. So with all this additional CPU power that you have, you're generating more and more CFD runs, more and more simulation results, and you need a way to look at all of that information all at once. So we've developed a product called Techplot Chorus to help with that. I encourage you to take a look at that product if you are doing a lot of simulations and need to look at all your data at once. You want to make sure that you're not missing anything, and it provides a nice user interface for bringing all your simulation results into a single product. Automation. This is really what we're going to be talking about today. PyTecplot was first introduced in 2017. And it's really opened up the doors for additional automation and additional analysis capabilities using the Techplot capabilities. And then finally, developer solutions. We have a number of capabilities for people who need to write Techplot data files, read Techplot data files. We can help you with custom solutions. We have Techplot Solution Services, which allows you to contract us to develop custom solutions for you. And then Python has made these custom solutions even easier. So a lot of people are starting to pick up the Python toolkit and develop their own custom solutions. We do have a great tech support staff, so we can help you with those as well. Okay, so on to the real subject of today's webinar is PyTecplot and the Python multiprocessing module, and I really like the Reese's analogy. It's like two great tastes that go great together. You know, PyTecplot has a lot of really great capability, and bringing in the Python multiprocessing toolkit allows you to accelerate your work and get your work done faster. So a little bit of background. What is PyTecplot? PyTecplot is an API to control Tecplot 360. You can see a link there which shows the documentation. This is a separate installation from Tecplot 360. So when you have Tecplot 360 installed, you don't automatically have PyTecplot. Because this is a Python module, you have to install it as part of your Python installation. We do require Python 2.7 or Python 3.4 and newer, and it has to be a 64-bit installation of Python. So all of that information is in the document. So we have a very nice installation guide that can help guide you through that. And then what is multiprocessing? Multiprocessing is a process-based Python threading interface, and threading is in quotes there because it's not actually using multi-threading, it's actually spawning separate processes. They can communicate with one another, but we're not going to go into that detail today. And you can see the link for the Python Multiprocessing Library there. So now this webinar today is we're not professing to be experts in the Python multiprocessing library, but we are going to show a method in which we have been able to use this library in conjunction with PyTecplot to accelerate the generation of movies and images. And this technique can go beyond just the generation of images. You can extract information from your simulation data as well. Okay, so with that, I'm going to jump into a demo, and what we're going to do is we're first going to define the problem that we want to solve here. In this case, we have a simulation of flow around a cylinder with a number of time steps, so this is a transient simulation. We're going to give a brief introduction to the multiprocessing toolkit, and then we're going to show how to use the multiprocessing toolkit in conjunction with PyTecplot. So let me jump over to another machine here to give you some background here. So what we're going to be looking at today is a simulation. This is about 145 time steps of flow around a cylinder. This is all in Plot3D file format. I believe the simulation was done with overflow, and each solution file is about 28 megs. So this is not a very large simulation, but it's going to be good for demonstration purposes today. So in this folder, I've created a Techplot layout already, which I'll load. Okay, and so let's take a look at the this data set and see what we have here. So the total data set, this is about 214 million total points. If we go into the time details dialog, we have 145 time steps loaded. And our goal today is to create a set of images of this simulation. So what's going on here is we've, number one, we've computed Q criterion using the calculate variables function under the analyze menu. And we have created an isosurface of Q criterion, and then we're just showing a slice down here colored by row. So at each time step here, as we're animating through, Techplot is loading this data, doing the calculation, and rendering the plot. So before we get into the Python side of things, let me just go into Techplot really quickly about animating to files or animating to images. One of the new capabilities that we've added in the 2018 R2 release is the ability to export to a sequence of images. This is really nice because you can take these images and then combine them into a movie. You can combine them into movie file formats that we don't necessarily support. We have some users who need to do GIF, and they're able to use a tool like ImageMagick to create animated GIF. So this is a nice little addition. One other frequent thing that we hear from people who are using Techplot 360 for animating to movies is, gosh, Techplot uses a lot of memory. And that can be true. Techplot is designed for use in the GUI, and we want to be as reactive as possible. So as we advance through these time steps, we're loading data and we cache that data in RAM. So you can go back to earlier time steps as quickly as possible. Well, when you're doing this operation in batch mode, you don't care about going back to the earlier time steps. So one of the optimizations that you can make in Techplot 360 in the user interface is go to the Options menu, Performance, Miscellaneous tab, and we have this Load on Demand section. So again, Techplot doesn't load all the data immediately. It will only load the data when it's required. And when we start hitting limits of RAM on your machine, we will start unloading the data that is the oldest in RAM, or the data that has been accessed the longest ago. So we have a bit of an aging algorithm there. Well, you can set this to minimize memory use, and that will unload the data as soon as Techplot can unload it. So this will really help with those long time animations. especially if you don't need to go back to those earlier time steps. So a little bit of background there. So again, our goal today is to export a sequence of images, and we want to do it faster than Techplot can do right in the user interface. So that's where Python and the multiprocessing library comes in. So let's start with a really trivial example. And this is a simple Python script that simply takes a set of values, so values 0 through 9, and we're going to call a function here called square value and print the square. So if I run this, you see it runs very, very quickly. We don't really need multiprocessing to speed this up, but let's just pretend that square value takes a lot longer. So we'll add an artificial delay in here and tell it to take 1 second per. So we can run square value, and you can see that it's taking 1 second per calculation for a total of about 10 seconds. So think of this as like Techplot. It takes a little while to load the data, it takes a little while to render, and we want to speed that up. So we're going to use the multiprocessing library. So let's bring the multiprocessing library in. So we'll say import multiprocessing. And this is, multiprocessing is a library that's part of Python 2.7 and Python 3. Today I'm going to use some of the capabilities that are only available in Python 3, but you can simplify your scripts to use 2.7 as well. Okay, so I've brought in multiprocessing, and then an important part of the multiprocessing library is we need to guard against this script running multiple times. So I'll explain this in just a minute. So we're going to put a little guard around here. And then we're going to tab all of these lines in. And what this guard does is it says only run this section when the script is initially run, and any other time this script is executed or imported, we're just going to have access to this function here. And that's important when we start using the multiprocessing library. Okay, so multiprocessing. So we're going to create what's called a process pool. And so we're going to say multiprocessing.pool, and we're going to tell it how many processes to use. We're going to say 10 in this case because I want to have this run. We know that we're using 10 values here, and I want it to run only in 1 second. So we'll create a pool of 10 processes, and then we'll say pool.map square value, and we're going to give this the range of 10, and then we can delete these lines here. Okay, so what's going on here is now we're creating a pool of 10 processes, so these are all going to execute simultaneously, calling the square value function. Each square value function is going to get called with one of the values in this range of integers, so 0 through 9. Again, this guard is to ensure that this block of code is only called once when I first execute the script. So let's hope that I don't have any typos in here. And there you go. So you can see that we've now used multiprocessing to accelerate this script on the order of 10 times. So it's now running in only 1 second. So that's what we would expect. And if we drop the number of processes, say down to 2, we should see this slow back down and take on the order of 5 seconds to run. Okay, so that's a really quick intro to multiprocessing. So that gives you just some of the basic idea. And now what I'm going to do is I'm going to jump into a more complicated script that is going to open this layout that we've created, and it's going to generate 1 image per solution time. So let me give a visual of what we're going to do with this script. So I'll go back over to PowerPoint briefly here. And so we have this script called Parallel Image Creator, and what that's going to do is it's going to create a number of processes. Each process, Parallel Image Creator, this script is going to be responsible for acquiring a PyTecplot license. It's going to open the layout to determine the set of solution times that we have in that layout. and then it's going to release the license and create a process pool. And so that's this pool here. Now, each process in that pool has the responsibility of acquiring a license, opens the layout just once per process, and then iterates over a subset of the solution times and will generate an image. And then when it's done generating all of those images, it will release the license. Okay, so that gives you a little visual. So let's look at the code. So again, we have this this guard here. We're going to, from the command line, ask for a layout file name to open and the number of concurrent processes that we want. We're going to do a little timing so we can get some information out to see how fast this works. Here's where we open the layout. So we're going to say new layout just to make sure that we're starting with a clean slate. We're going to open the layout file. And this here, if you haven't seen PyTecplot yet, these are the PyTecplot commands. So this is actually using the Techplot 360 capabilities within the Python script. We're going to reach into the data set of our active frame and ask for the set of solution times. And so we store that into a list. And then we're going to give a little bit of information about how many solution times we have. And then we're going to call stop. So this is going to be responsible for releasing the PyTecplot license, because we don't want to hold on to more licenses than we need to. And I'll discuss the licensing of this later in the presentation. Okay, this is an important distinction here. PyTecplot does require that each of these processes is a completely separate independent process. On Linux, the default is to fork processes. We need to use spawn, so that's a bit of trivia here that's important to know. Again, this script will be up on our GitHub, so you can download it freely shortly after the webinar. Here we're creating the process pool with the number of processes, just like we did over in the square value script. And we're going to open the layout once per process. So that's what this initializer is doing. And we'll look into the initialization function in just a second. And then here we're using the same sort of function that we used over in square value. Over there we used pool.map. This is a slightly different version called star map, which allows me to write this save image function that takes multiple arguments instead of just a single argument. And then when this script is done, we're going to close and join the pool, which allows Techplot time to clean up all of the binaries and shut down appropriately. Okay, so this is fairly somewhat generic code here. So let's look into the actual work that we're doing, which really isn't much. So we'll start with the init function. So each process, remember, has to open the layout, and we only want to open that layout once because opening a layout with 145 time steps can be somewhat expensive. So we're going to do that here. So for each process, we open the layout file. As I showed earlier, we're going to use that unload strategy of minimize memory use to keep the RAM low. And then when this process is done, again, we're going to call stop to allow Techplot to clean up some of the memory and release the Techplot license. And then for each process, we're going to be iterating over a number of solution times. In this case, we're going to, now that we already have a layout loaded, all we have to do is set the solution time that we want to advance to. We construct an image file name. This is going to construct an image name that has numerics, so it's going to be like image underscore 0000 0001. And that works really well with the FFmpeg library to combine these images into a movie file if you want to do that after the fact. And then we call a PyTecplot function to save it to an image. Okay, so again, this script's responsibility is to figure out how many time steps we have, create a process pool, and then for each process in that pool, we're going to iterate over the solution times and export an image for each solution time. All right, so let's show that how that runs. So we'll say parallel image creator, and we'll go to that layout file that we have, cylinder.lay, and we'll tell it how many processes, concurrent processes to use. So this is an important aspect of using multiprocessing, is you kind of have to know the size of your data, the limits on your machine. So this machine that I'm on has 24 logical processors, 12 physical cores, and 32 gigs of RAM. And we're working off of the H drive here. We have 2 drives on this machine. The H drive is a spinning disk, so you need to know, how fast is your disk, how much RAM do you have, and how many CPUs do you have to understand how many cores you can use. Okay, so we'll run with 12 cores, so that's half of the total CPUs that we have. Okay, so we've executed this script. It opened the layout and found that we have 145 time steps, and we've started up 12 processes. Now, we can see now that the images are getting created kind of fast and furious here. So if we go to, if we're on the Performance tab, we can see that we have fairly good CPU utilization. We'll go over to Processes, and we can see under the command prompt we have our 12 processes here, each one using some CPU. This is the interesting part here. You see that I'm using 50% disk. Well, I have 2 disks, so this actually is showing that my one drive that all of my data is on is completely flooded. So at this point, I'm I/O bound. So throwing more cores at this problem, more processes at this problem, is not necessarily going to speed it up because I've hit the limits of the hardware on my machine. So really, again, really important thing to know. I'm nowhere near the memory limit, so I could do a larger problem. I could try to do more in parallel, but I'm not going to get that much better scaling out of this problem. This should take about 60 or 70 seconds to run, and we're probably 45 seconds or so into it. So let's just wait for this to complete. Okay, so it took 90 seconds that time, so a little longer than I'd said, but you can see that we got through that fairly quickly. Now, if I do this again and say just one CPU process, we'll see that this is going to go by much slower. So you're just going to see one image and then another and then another. And in my playing with this data set, it would take on the order of 4 or 5 minutes. So on this machine, we were able to get about 3 to 4x faster using this multiprocessing. And this script, anyone can use this script if you have PyTecplot installed. So a very generic script for any layout that you save. So you can see how much slower that's running. Okay, so let's jump back into the PowerPoint, and let's talk about some of the results that we got and some of the ideal parallel use cases. So what we showed here is a transient case, and that's really where this multiprocessing is going to be really helpful. Now, we have had some users take advantage of this for other items like extracting a lot of lines from a steady state solution. It works well there, or a lot of slices from a steady state solution, but really transient is where the real benefit comes in. So transient data where each time step is in a separate file or in one file works really well, and where post-processing relies heavily on single-threaded portions of the data processing pipeline. So you may wonder, why, Techplot, why don't you guys just multi-thread everything for me? And the truth of the matter is, some of this is very, very difficult to multi-thread. So running in this multi-processing mentality works really well. So, particularly file I/O, getting data off the disk, it's really challenging to multi-thread. Some calculations are just inherently more difficult than others. So this really helps out with some of that. Rendering itself is single-threaded. You have one graphics card. But you can get some process parallelism using this technique. Okay, so some of the results, this flow around the cylinder, what I showed you today is just a few time steps of the overall case that we did. This was a structured data set, about 1.3 million cells per time step and 1,400 total time steps. There's about 40 gigs on disk, and this one was interesting. We didn't get really any scaling between 1 and 2 processors. And I think that the reason there is some data loaders, some data formats are a little bit more expensive to load than others. So the Plot3D file format, Techplot, it doesn't supply min and max values, so Techplot does have to scan through a file to do some additional calculations on first load. But we started seeing scaling after 2 processors. All of the results that I'm showing you here were on a different machine that had also 24 cores, but 128 gigs of RAM. So you can see that this one scaled up to about 16 cores. We got a 5.3x speed up, and we went from nearly 90 minutes down to 15 minutes to create this animation. The next result, this is an internal combustion engine, courtesy of Convergent Science. They use an adaptive mesh refinement technique and polyhedral cell types. So on average, we were about 500,000 cells per time step, 266 total time steps in Techplot PLT format, about 70 gigs on disk. And you can see that with 1 core, we were at about 31 minutes, and at 16 cores, we got it down to about 5 minutes. So I like to say that you can get your work done during your coffee break now instead of your lunch break using this technique. So we had about 7x speed up. You do see that the RAM does creep up quite a bit, and this is because we are loading many of these simultaneously. So you do have to be aware of the RAM limits on your machine. Hey, this is a simulation of Seiko Bay, which is from FVCOM, courtesy UMass. You can download the data there if you want to. It's 168,000 cells per time step, so this is really the smallest data set that we had, at least per time step, but 3,000 time steps, so it was about 22 gigs on disk in FVCOM format, which is a NetCDF data file format. And this one, we actually got incredible scaling on this one. We got all the way up to about an 11x speed up. So from 3 hours down to nearly just under 16 minutes. So you can see that you can get some really good scaling here. And I think that a big part of the scaling here is because it is a pretty small data set per time step. So there's just not a lot of data to load there. Excuse me. And some of you may have seen this animation on social media a few weeks ago. This is a data set that is courtesy Los Alamos National Labs. They created this data set for purpose of understanding a deep water asteroid impact, to understand whether it would create a tsunami that we needed to be concerned with, and what it came down to was no, the ocean's pretty good at absorbing impact from asteroids. So those of you in the coastal cities can be rest assured that you're going to be okay there. But this data set, 27 million cells per time step, structured data. We had 476 time steps. This actually came in a VTK format, which we then converted to Techplot's SCPLT format. It was about 707 gigs total on disk. And you can see that we got nearly a 6x speed up here as well. One of the oddities here was the number of processors. At 1, we had 22 gigs of RAM, and I'm still not quite sure why we had high RAM in that case. So a little bit more looking into that, but you can see that these other cases where we were running in batch mode with PyTecplot, we had some good scaling and got the time from 15 hours down to under 3 hours for creating this animation. This is a really complex animation for us to make here. We're using a technique here. It's not volume rendering, but it looks kind of like it. We are rendering, I think it was on the order of 30 or 40 isosurfaces with a high degree of translucency to get this look. So we're actually loading quite a lot of the data in this case to generate that complex isosurface. Okay, so I said that I would talk about licensing a little bit. So who can use PyTecplot in parallel? Well, number one, you have to be paying for Tech Plus. So Tech Plus is our support and maintenance contract. And with Tech Plus, you get access to PyTecplot. So when you buy Techplot 360, you're getting Techplot 360 itself, but then our maintenance gives you access to PyTecplot as well as Techplot Chorus. So if you have a single user license, you're allowed to run as many instances of Techplot 360 or PyTecplot as you want on that single machine. So you can, again, get a high degree of parallelism, which was what we were doing in these examples. If you have multiple network licenses, you are limited to the number of seats, but when you are paying for maintenance, you have for each floating license, you have 1 seat of Techplot 360, 1 seat of Techplot Chorus, and 1 seat of PyTecplot. So I know that some of our larger commercial organizations, you make sure that you're using PyTecplot because you have a lot of utility there. So you're effectively getting 2 instances of Techplot 360 capability for your maintenance. Because you can run PyTecplot in batch, leaving the GUI licenses untouched. So really high value of maintaining that Tech Plus contract. And then this is going to be biggest benefit to users with, say, site licenses or high seat counts. So some of you at, we know that some of our customers have access to large seat counts, particularly a lot of our academics. And then single user licenses, if you have Techplot 360 and PyTecplot installed on a machine with high RAM and high CPU count, you'll be able to get some really good scaling. Okay, and just to kind of round out some of the benefits of using Techplot 360, we allow you to easily explore and interact your large data set with your large data sets. We have some people in the geosciences who are new to Techplot 360 coming from 2D tools that only allowed scripting, and they're saying, wow, I'm really able to see my data and make sure that I'm not missing anything because I'm looking at it in this volumetric way. You're able to automate with PyTecplot, as we showed today. Get recognized with high quality raster and vector export formats. I've had a lot of people say, man, when I do a presentation, I have to use Techplot because it has such good rendering and the plots look so good. And then support is here when you need it. That's one of the big benefits of paying for support is you can call us up, you can send us an email, and we're here to help. We're here to help author some of these Python scripts to help you get your work done faster. So our support staff is available in the US, 6:30 a.m. to 5 p.m. Pacific time. We also have an office in Germany available during regular hours there, and then worldwide we have local distributors that can help with tech support as well. And then here are some nice customer quotes. The one on the bottom here, this is a game changer for me. This is one that occurred recently when we introduced this capability, this multiprocessing capability to one of our users. The one in the middle, we do have really good tech support. That's one of the things that I really love about Techplot. We're on first name basis with a lot of our users, so please do give us a call, send us an email, and we'll help you out. So that's really the end of the presentation. I do want to open it up for any questions or comments during this time. This has been a lot of fun for us to help people get additional capability out of Techplot using our Python API and using some of these tools that are available in Python. So I will reiterate, a question came in, will this webinar be recorded? Yes, if you joined late, this is being recorded. The scripts are going to be available in a couple of days on a GitHub link, which I'll show in just a second. And yeah, we'll send out the recording. So there is one other question here. Is PyTecplot included in the package of Techplot for Converge? Good question. So last year we partnered with Convergent Science, which makes a CFD code that is used quite heavily in internal combustion, but they also can work with many other application areas such as gas turbines, external flows, etc. And in our partnership, if you do buy Converge, you get access to Techplot for Converge for free. That toolkit allows you to use PyTecplot, but only when the Techplot 360 GUI is up. So our PyTecplot API does have the capability of not only running in batch mode like I showed today, but also driving the Techplot user interface. So if you do want batch mode capability with Techplot, you're going to have to upgrade to a full license of Techplot for Converge. Okay, so not a lot of questions today. Thank you for your attention. Oh, here comes one. Does it run well with other softwares like StarCCM? So we do not have a direct loader for StarCCM, but StarCCM can export in CGNS format, EnSite format, and Techplot format. So we do have loaders for those. So take a look at those export formats, and we'll be able to load those quite well. Okay, is session.stop required to clean up the temporary files? Can't you just let the process exit? Yeah, so yes and no. So one of the things that we noticed on Linux is we get a crash or a core dump on exit. The multiprocessing toolkit just terminates the process, and you'll get a core dump on Linux. So it really is important to call stop to make sure that Techplot closes before the multiprocessing library terminates the process. Here's another question that came in. Let me just have a chance to read it. In some cases, double the processes resulted in more than double the total RAM. How much have you explored memory usage with this? It's a good question. That sounds like something that we'll have to look into a little bit more. In my testing, I was seeing a pretty linear scaling with doubling the processors. Now I was doing everything on a single node, single machine. So I'm not sure. Maybe we can talk later on that. And can I use a GPU for calculation? No, the Techplot does not take advantage of the GPU in its calculation, so there's no way that you can use the GPU. Okay, back to the RAM. So let's go back to some of the numbers. Person who's asking the question on posted numbers for the RAM, do you happen to remember the slide number? We can go back and explore that a little bit. So in some cases we were getting more than double the RAM. This is, let's see, yeah, from 2 to 4 we had more than double the RAM. So yeah, good question. So 14 to 30. I did do some rounding on these, so it might have been 14 and a half and 29.8. So that might be some of the issue there. So yeah, not exactly linear scaling here. And when doing these tests, I was also looking at the process monitor. So this is not an exact science. So I was trying to do just totaling up the RAM per process, and it fluctuates quite a bit. So there is some error in these RAM numbers, but they're close. So. Okay, well, thank you for your time today. I've enjoyed doing this webinar, and thank you for all the interesting questions. So PyTecplot we have available here, techplot.com/PyTecplot. All the PyTecplot documentation is available on the second link. GitHub, we've started an area where we're starting to accumulate Python scripts and some Techplot macros at this location to help our users out. We have some organization work to do out there still, but if you have any questions or need any PyTecplot help, we have some good examples out there for more complex workflows in the PyTecplot documentation. We have some really great examples as well. And then if you want to learn more about the Multiprocessing Library, go ahead and follow that link. Multiprocessing is a pretty neat toolkit, and there's a lot of capability there that we didn't touch today. Thank you very much.